Hello everyone, welcome to lecture 4. This is the first installment of this lecture, and in this lecture we are going to start talking about systems of linear equations. Now this topic is going to continue on for at least a couple more weeks and maybe even more. So this first video is all about the instructions. These are very basic stuff and going to be very easy. So let's begin. We are going to start from again the basic question of what exactly is a linear equation. Now the word linear here kind of hints at the suggestion that these are perhaps equation for straight lines, something like y equal to mx plus c, our very familiar formula for straight lines. And let's bring out a graph. So this is a straight line and the formula for this line is y equal to 1.5x plus 2, so in the format of y equal to mx plus c. If we want to write it in the more standard form, that is ax plus by plus c is equal to 0, the formula becomes 1.5x minus y plus 2 equal to 0, the formula of the straight lines. So yes, I guess you can think that the equations that represent straight lines are perhaps called linear equations, and that's not exactly wrong, because this is in fact a linear equation. And to be honest, if you go on the internet and search for what a linear equation actually is, a lot of the answers are going to tell you that these are the linear equations, the equation of a straight line. But that is not entirely correct either, because looking at the equation, how can you tell that yes, this equation is of a straight line, or no, this is not the equation for a straight line? You can't exactly tell that just by looking at the equation. Let me show you something. So let's think of the equation x equal to 3. Now as we saw earlier, this is a linear equation because we can write it in the form ax plus by plus c equal to 0. In this case, a is 1, b is 0, and c is just minus 3. So this is supposed to be the equation of a straight line, but when you are in the single dimension, the one-dimensional line, x equal to 3 is just a point. When you go to the second dimension, that is the two-dimensional plane, yes, the equation becomes the equation of a straight line. But if you bring out another dimension, I'm just going to cut off the negative part of the x-axis here. If you bring out another dimension, this equation x equal to 3 becomes the equation of a plane and not a line. So you can see that as we are going to the higher dimensions, the equation x equal to 3 started representing a point, then it went to a line, and then a two-dimensional plane. If you go to the fourth dimension, x equal to 3 will represent a three-dimensional space, and as we go higher, this same equation is going to continue to represent more and more complex geometries. So we cannot really define linear equations by the statement that the equations of a straight lines are called linear equations, because that won't be a correct or complete statement. So how exactly are we going to define a linear equation? Here is the answer on your screen. Linear equations are defined by this formula. An equation that you can write in the following form, you can call that equation a linear equation. And in here, x1, x2, x3 are just variables. You are probably more familiar with x, y, z, and so on. And all the other things are coefficients. In most cases, they are going to be real numbers. So the only thing to notice here is that none of the variables have a power higher than 1. The power of all the variables has to be 1. So we cannot have x square or x to the power 4 or x cube. We cannot even have x to the power minus 3 or x to the power half. Now let's see a few examples of equations like this. So all of these are linear equations. In here we have x equal to 3. We have two variables here, 2x plus 3y plus 4 equal to 0. We have three variables here. We have three variables here again. And we have four variables here. This one right here is not a linear equation because we have x to the power 2. The power of both variables x and y is 2 here, which is a violation of our definition. So the last one here is not a linear equation. Now none of this should be new to you because you have used linear equations many times in your life, all of you, in your high school or college or just in general real life. But we are still going to give you one more example of how many real-life scenarios can be modeled into linear equations. So let's say we have our two hobbits, Frodo and Samwise, who are going out on an adventure. So as hobbits like food, Frodo decides that he's going to bring the chickens and Sam will bring the cakes. So let's say we have two variables, number of chickens and number of cakes. Damn, that cake looks good. Anyway, so now let's say the chicken cost 4 silver coins and each cake costs 2 silver coins. We also know that together they have spent 14 silver coins in total. So we have a linear equation here. 4 into number of chicken plus 2 into number of cakes equal to 14. This equation is basically 4x plus 2y equal to 14. I just used a couple of silly pictures to make the slide look colorful. Anyway, so what is a solution for a linear equation? Well, the values of the variables for which the entire statement becomes true is a solution for the linear equation. For example, if we put 3 chicken and 1 cake here, we have got 4 into 3, that is 12, plus 2 into 1, that is 2, equal to 14, which is the correct statement. That means 3 as number of chickens and 1 as number of cakes is a solution for this linear equation. But this is not the only solution, because I can also put 2 chickens and 3 cakes and still get a completely true statement. 4 into 2 plus 2 into 3 will again get me 14. So we have a lot of solutions here. And if we allow fraction values or negative values, we'll actually get infinite solutions. So let's put another information in here. Let's say we know that the number of chicken and the number of cakes is equal to 6. Now together these two informations tell us that the only possible solution for these two statements both to be true is when the number of chicken is 1 and the number of cakes is 5. So apparently Frodo didn't bring much food at all. Sam brought a lot of cakes. Anyway, so the point of this story here is to get a unique solution of a system of linear equation. By the way, a system of linear equation is nothing too complicated. When you have a bunch of linear equations together, they are called a system of linear equations. For example, in our last example, we had two equations and together they made a system of linear equations, and from that system we got the values 1 and 5. Alright, so to get a unique solution for a system of linear equations, we must have at least as many equations as the number of variables. So what I'm saying is, if you have 3 variables, to get a unique solution, you must have at least 3 equations. If you have 3 equations, you cannot guarantee that you will get a unique solution every time, but without 3 equations, if you have less than that, you can guarantee that you will never get a unique solution. Okay, so let's see a system of linear equation using numerical terms and not Sam and Frodo's chickens. So we have 4x plus 2y equal to 14. If I plot this graph, this is how we have solved system of linear equations so far in our entire life. So in this two-dimensional space, this equation represents a line. We also have x plus y equal to 6, the second equation of the system, which gives us another line. And the point they intercept in, this is our solution point. So as you can see, our solution point is 1, 5, which is consistent with what we got earlier. 1 chicken, 5 cakes. Now, sometimes we can have contradictions. So we have 2 equations here in the system. We are getting some information from here and some other information from the second equation. Sometimes these equations are going to contradict each other. In this example, let's say the first equation is x plus y is equal to 3. This is clearly a contradiction because the first equation is saying x plus y equal to 3. Second equation is saying no, x plus y is equal to 6. So our lines is going to look like something like this, parallel lines. And we know that parallel lines are never going to meet at any point, which means no solution exists. Sometimes we can also have infinite solutions. And the obvious case is when the number of equations is less than the number of variables. But even when we have as many equations as the number of variables. For example, in this case we have 2 variables and we have 2 equations, we still can get infinite solutions, because even though it looks like we have 2 equations, these are dependent equations, just like we saw in linear combination. Because if you notice, multiplying the first equation by 3 will get you the second equation. So this is actually not a second equation. This is just some scaled value of the first equation. So if we plot the lines here, they just become the same line, and every point of that line is a solution. So we have infinitely many solutions. Now, the point to note here is that a system of linear equation can have only 3 cases. Number 1, they can have one unique solution. Number 2, they can have no solution when the equations are going to contradict each other. Number 3, they're going to have infinite solution. There is no case in anywhere in the world where you will get a system of linear equations that will have like 4 solutions or 5 solutions. If you get more than one solution, you can pretty much guarantee that there are infinitely many solutions as well. Anyway, so let's look at a 3-dimensional case. We have 3 equations here. The first one is x plus 5y plus 2z equal to 5. Now if I plot this linear equation in a 3D space, as we saw earlier, we are not going to get a line, we are going to get a straight plane. And this is the plane. Now let's plot the second equation. And the pink one is the second equation. As you can see, we have only 2 equations for our 3 variables so far, and that is why they intercept in a long infinite line, and every point in this line right here where they intercept each other is a solution. So we have infinitely solutions so far. Now let's put on the third plane. Okay, so this orange plane represents the third equation, and now we have only one specific point. So this point right here, this point is our solution for this system of equation that consists of 3 linear equations. If we had parallel lines, so instead of this third equation 2x minus y plus 2z equal to minus 17, if I put a third equation that contradicts my previous equation, like 7y minus 10z equal to, instead of 15, I'm going to say minus 10. So the second equation and the new equation are going to contradict each other, and let's see how it looks. And as you can see, we have 2 parallel planes that will never meet each other in a single point, and that is why this system of equation has no solution whatsoever. Now let's come to the point where we can represent a system of linear equation using a matrix. Now each of these equations have a specific structure. We have something into x plus something into y plus something into z. All of these equations follow the same structure. In the second equation, we don't have x, but we can just say we have multiplied x with 0. So 0 into x, we can just say 0 into x plus 7y minus 10z equal to 15. Which means to express an equation, we only need the coefficients, and that is how we represent a system using a matrix. Each row in here represents an equation. The first row is 1, 5, 2, which means the coefficient of x is 1, we have 1. Coefficient of y is 5, we have 5. Coefficient of z is 2, we have 2. Similarly, 0, 7, minus 10 represents the coefficient 0, 7 and minus 10, and similarly 2 minus 1, 2 is 2 minus 1, 2. But as you may have noticed, we don't have the right hand side of the equations, and that is why we are going to use this matrix where we draw a bar and write the right hand side of the equation on the right side of the bar. This is called an augmented matrix. We are going to see how to solve linear equations in the future, and we are going to learn more about this matrix representation in the next video. I'm going to stop here today, and I hope that was pretty easy. I'm going to see you on the next video very soon. Until then, thank you and take care of yourself.